Now, Signal Processing Society, and I'm Lou. I'm the chapter vice chair from Brunel University of London. And then later on, we will hear the talk from Professor Asoke Nandi on Age of Data, a personal journey. So you know that signal processing will deal with lots of kind of data. And Prof. Nandi, he is on the Royal Society of Engineering Fellow. He's also fellow of IEEE, and then throughout his career, he has processed different kinds of data, because some of my colleagues mentioned that communication data, some mentioned about biomedical data, so he has a lot to share with us today. All right, so, and then we'll just say, before we start, we just tell everybody, we're going to start to record this session soon, okay? So that's just following the UK that we will, sorry. Okay, so I'm going to start to record. Oops. It's already recording. All right, so we start recording this session. And if your camera is on, please be mindful that you may be recorded. And also your microphone is mute if not speaking, because otherwise there will be some interference. If something goes wrong, don't get panic. We will have something like admitting attendees. And if something isn't right, especially the AV service, hopefully not, will pop up and then pop back in. Okay, so the AV settings, we already checked, they work fine. Okay, and I also checked with the audience online, they seem all right. Okay, so, and then we have a very brief introduction about the Signal Processing Society. Yesterday was the International Children's Day, and then today we're going to celebrate IEEE Signal Processing Society, which was first founded in 1948. So today we are celebrating its 77th birthday. Currently, we have about 3,000 members in more than 120 countries. And of course, we have some activities like publications, you know, that we have these IEEE transactional signal processing and related journals like image processing and audio. So we also have some conferences, and the flagship one is the ICASP. And this year is the 50th anniversary for the ICASP. Prof. Nandi just gave a wonderful talk there as well. We also have, say, different kinds of workshop like this one. We have distinguished lecture and also distinguished industrial speaker program. And we hopefully, in sometime in future, we also invite some of the industrial speaker to present a seminar for this society talk. SPS challenging program, webinars, short course recordings. If you log on to the Signal Processing Society website, you can see all these sorts of things. And of course, that we want to encourage people to join our society. Okay, so this is who we are. So James, not sure whether he's here today. James is currently chair for the UK Ireland section, and he is a professor in University of Edinburgh. His main expertise is on statistical signal processing, and I'm the vice chair from Brunel University, and my main research focus is on the sampling and reconstruction, but recently I'm also working on machine learning. George, he is secretary and treasurer, who is in charge of the money, and he's from University of Surrey, and he is a member for Institute of Communication System 5G 6G Innovation Center. All right, so we try to work together to bring all members from this Signal Processing Society, mainly UK, but we also share our experience with Signal Processing Society in other countries. All right, so this is our plan for this year. Let's say, like, we have hybrid talk every 2 months. The one in April is on the large language model and for audio signal processing from Professor Wenwu Wang in Surrey, and today is a talk from Professor Asoke Nandi. And if you want to present a talk, just email one of us, and now we really welcome volunteers. distinguished lecture talks that these will be, say, arranged later on, and also online early career researcher talks. So those are, say, including those PhD students and postdoc research associates or research assistants. Okay, so we want to give the early career researchers some opportunity to present their work to the signal processing community who perhaps otherwise don't have other, say, seminar opportunities. All right, so anyway, so we are very open to your suggestions, and feel free to email us. Okay. So, and we also say prefer that if you are currently a member, then we welcome you to apply for senior membership. And likewise, if you are already senior member and you think that you're capable enough, we welcome you to apply for the IEEE fellowship. Okay, so, and we are still, say, developing full program events, and we'll share on our website. Okay. So, and then because this research seminar is also funded by Brunel's AI Research Center, which Tatiana, director of the research center, she provided a coffee, tea, and cookies for those who attend these research seminar in person. So just leaves Tatiana to have a brief introduction about our AI Research Center.
Good afternoon, everyone. So I'll just briefly introduce our research center on AI, social and digital innovation at Brunel University, London. The unique point of our center is that we are assembling our under umbrella STEM and social scientists. It's allowing us to complete truly interdisciplinary research and develop methodology where we can integrate STEM and social scientists together under the same umbrella to look and understand how we work together. And it's not only advancing the new technologies, but also looking on how innovations can be truly guided in the most efficient ways into business processes. So we will, our center is basically land on 3 pillars. We are looking on applications, but we are looking on green, environmentally friendly applications, where we are looking on not only utilizing AI efficiently in particular applications, but we are looking on green and energy efficient AI models and developing the techniques that will provide us energy efficiency with deployment of AI. In addition to this, we are looking on how to integrate AI in very responsible and trustworthy way, making sure that it has been accepted at society level and provides a sufficient level of reliability in critically sensitive applications. Here I will just provide you several examples of current project which has been secured in the last year by the center. So you could really see we have a wide variety of work carried out in AI from perspective of technical perspectives, looking on responsible frameworks and green AI in terms of number of applications such as condition monitoring in maintenance to for example, craft image analysis. Towards also we are looking on in terms of LLM metrics for trustworthiness and faithfulness, ensuring that they can be acceptable in critically safe safety applications. At the same time, we are looking on responsible frameworks in applications, such applications like heritage and IP. So our expertise is really interdisciplinary. We have quite a few projects developing now, and we are working on at the level of interdisciplinarity, where we have social scientists and STEM engineers working together. And if anyone is interested to collaborate with us, we are open for collaborations. And thank you very much for inviting. Thank you.
Right, so I will change the slides and just close more slides and then Right, so I have just to change the slide. Sorry, can someone just have a quick check whether you can see that this changed the slide, and then we're going to say let Prof. Nandi to present the talk. Yeah, can you see the change slides? That is now, so it should appear on your screen. New set of slides. Age of data, of course. Yeah, can someone just go log down and then, yeah. All right, thank you. So then I'll pass it over to Prof. Nandi to do the presentation. Just, yeah.
Okay, good afternoon from London. And I'd first like to thank Dr. Lou Gan, and I think the UKRI section of signal processing would be a great success, I'm sure. And it is a special day in the sense that this is the 77th birthday of the IEEE Signal Processing Society, and there have been many, many signal processors, well-known signal processor in UK, among others. And so it's quite right that we should celebrate it. And I also like to thank Tatiana for hosting this event. There are in the department, as you saw, 2 candidates here, Lou Gan and Tatiana, but there are many others who are working in signal processing or AI or both in combinations. There is quite a lot of strength in different, and you also saw a list of projects from Tatiana. There are many names from IEEE there. So today, I'm going to tell you about age of data. The so-called big data have become a big thing, particularly in the last 25 years. But for me, I feel I've always worked with data and always worked with big data. So, of course, big then and big now, they're different sizes. So, but I like to take you through some of the things that I've done and relates to signal processing and AI. And it's because, and these topics, I say personal journey, I've taken from my own journey, partly because I know them very well, I like to think. And secondly, because they are spectrum, it's a rainbow. So I didn't work on just 1 or 2 topics, I worked on many topics. So it's a way to show that there are many different things that can be done. And I particularly welcome the young people because it's an enormous opportunity. I was at the ICASP that Lou said, which is the International Conference on Acoustic Speech and Signal Processing. This is the 50th anniversary of that conference. And if you want to know the strength of signal processing, I'll invite you to go to an ICASP maybe next year. This ICASP this year was held in Hyderabad for the first time in India, and there are 4,000 registered, about 4,000 registered participants in that conference. And there's plenty of people from industry. And it's, as Lou said, I think something like, is it 23,000 members? And so it's a very, very strong society in terms of participation. And so it's there's plenty of things to be done. But you know, when something is old, like this, 77, I have a lot of respect for things that are old. Not because they're old, but it comes with that. And the reason is, if something is old and still survives, the world around it changes. That means this thing, this entity has to adapt with passage of time. And if you don't adapt, then you die. And that's what Darwin's theory of evolution tells you. And this, the fact that something survives this long, that means they have adaptability. So when I first started doing AI, I have always been a member of the Signal Processing Society. Hardly anybody in signal processing was doing AI. But now you get plenty of papers in AI in the signal processing society. So that's the kind of part of the adaptation that I mentioned. Okay, so I move on. So these, I'm not going to go through everything here, but this is the few of the topics that I'll pick out and tell you about it. Which I put that up not to discuss each one, which I will discuss in a minute, but just to give you the idea that there are many different things that can be done. And these are not the exhaustive list by any means. As I said, that's just my personal journey, and even somewhat selected. There are other things that I've done, but this should make the point. So first is about this is kind of introduction of me, but what I want to say is this last bit. Yeah, you can see the arrow. So research is not about numbers, because numbers come after you have done the research. So numbers are really output, and in fact long after the output. But so for me, research is always about finding things that are challenging for me or interesting, or I can learn from them, but it must be fun. Without fun, it's no good doing the research, because you're not going to give your best to it. And but I think research is also for me more than that. Of course, that is the first reason, but the second reason is to influence people. So that not only I find something interesting, I want to convince you, and as many of you as I can, that it's interesting. So its influencing is important as well. But the primary reason is about basically satisfying my soul, if you like. So just a slide about what signal processing is, in case someone needs to know, but is that, of course, it's my personal view. I think in signal processing, it's not quite right. I take some license to make this slide. I think there are three fundamental problems in signal processing. One is detection. That's to ask the question, is there anybody in this room? And the answer is binary, yes or no. That's the detection. And two is estimation. If we think there are, how many people are there? That's the estimation problem. And three is the prediction problem. That is, okay, so we got so many people in this room now. How many will there be in this room tomorrow or next week or whatever? So those are the three fundamental problems in signal processing. Now, of course, one time I was telling, not this exact lecture, but this kind of slide, somebody asked me from the audience, so what do you think coding is about, image coding? And coding is clearly about prediction. I'm not saying everything can be put into this, but pretty much signal processing is just that. The other thing, I take even a bigger license to say, I'm old enough to do it, is that it's very, very fundamental. I'll go more beyond that, that life could not exist without signal processing. In the sense, you get hungry and you need to realize you're hungry, then you can have some food. And then depending on how hungry you are, you might have bigger amount of food or lesser amount of food. And tomorrow you don't know if you'll be hungry, but you predict that you'll be hungry. So you actually buy your shopping beforehand. So this, or if you want to cross a road, you want to know, are there any cars coming on either side? That's the detection. And estimation is, there may be a car coming, but there may be a big enough gap so that you can cross it. Or maybe there isn't, so you don't cross it. So that's estimation and prediction. So I think truly that life could not exist without these signal processing. And birds and bees do it as well, and plants do it. There are some plants in desert which store up water because it's desert and there are times when it's much hotter than others and such things. Anyway, leave that aside, but it is fundamental, I believe. AI, everybody knows about AI. When I started doing AI, about 30 years ago, then even some of my colleagues in the department, not here or somewhere else, didn't know what I was doing. But now everybody in the street knows what AI is. So that's how the world has changed. So for me, one way of seeing AI is about discovering structures. Of course, they are not structures in the sense of solid things, but it could be. But they are about data structure. And it's also about discovering rules. You might be playing a game, chess or whatever, and you can concoct AI so that it looks at the games as it's being played and it will tell you at some point what the rules are. So you can discover rules. And of course, the biggest thing is application. So every country is trying to make a business out of AI. And so that's where the sort of everything. Of course, the much more fundamental things are happening somewhere else. Okay, given those two, I come to my first topic. And this, I'll read it for you, is clear, is W plus, W minus, Z0. And the plus, minus, and zero refers to charge of a particle. And these three are three different particles, and they are called fundamental particles in physics. And these things, so if you go back 1975, we didn't know whether they exist or not. We didn't know, we knew they might exist, but we didn't know that they exist. And so because of that, we were unsure. But then sort of things happened, and I had an opportunity, and I'll come back to this point, to actually work in here. And then this CERN, CERN, is an organization in Switzerland, is the European Center for Nuclear Research, but most of the research is actually particle physics. But that's how it started. And then in 1982, what you're seeing is called an event in their language. And what is the event? Event is there are two particles, one coming from your left and the other coming from your right, and they collide. And it's like two cars colliding head on. And when they do collide, it creates an enormous bang. And basically, it creates lots of new particles. That's what happens. And when those particles are created, most of them are things you know, but there is a chance that you might get some new ones. And these particles happen in the context that I want to bring in the big data. At the time, this experiment generated biggest amount of data than any other place in the world, which is small. Today is kind of, but nonetheless, that was the biggest. And the collider, that's not the physics, well, there is a physics bit, but the machine that makes it happen, we're not sure that will work. And in fact, I won't mention it because it's being broadcast. There is a very famous physicist, US physicist, sent a telegram to CERN because we asked them, various few people, what they think of this project. And this person said, it won't work and we'll never discover W. But nonetheless, it was done. And we did discover. So what happens is that this also had, these Ws, they live very, very short time. Basically, they die as soon as they're born. They die less than millisecond, less than microsecond, less than nanosecond, and less than femtosecond, and so on. So we can't see them. We see their children. And there are many types of ways they can decay. One of them is electron, which is a negatively charged particle, and the whole world depends on that. There will be none of this without the electron. And neutrino, this is a neutral particle. And what we see is we have to work backwards, So this is this pink arrow is put in. This particle is electron, and neutrino don't leave a trace because it's neutral, and this is an electromagnetic field here. So neutrino is not seen because they don't interact and they got no charge. But this is seen because it's got electromagnetic charge, and there is electric field and magnetic field in here. So, and this was the first W that was seen was seen in a court by humans. And that was 1982, December. And then few months later, in 83 April, this is a different kind of graphics, but it's the same thing. Particle comes from left, particle comes from right, and they collide, and then they produce lots of stuff. And in this case, you create this Z0, and again, they don't live long, just like Ws. They die as soon as they're born, but we look at their children. And this is an electron and a positron. And we just deduce that the case, the Z0. And so that is, and why they're significant is that these three particles, just like you see me through light coming onto my face, and light is photons, and then is getting to your retina, and then your brain makes a face out of all these photons that gets to your retina. So, but the more important thing here is that the photon is the carrier, is the messenger of electromagnetism. And these are messenger of what used to be called weak nuclear force. And more than that, it turns out that they actually is just like electricity and magnet. If you go back before James Clerk Maxwell, if you go back to 1870, electricity and magnetism are two different forces. But Maxwell combined, unified the two through the work of, another physicist, Michael Faraday. And we have electromagnetism. And now we have electroweak force, because weak force and electromagnetism, they're not different forces. They are they're not completely different. They are cousins. They are cousins. So electricity, magnetism, they're cousins, and so is electroweak force, they're cousins. So now we have, and this was very fundamental to the understanding the forces of nature. But that said, looking back, it was kind of a fairy tale years, because 1979, I joined this experiment from Cambridge. I finished my PhD and I started. And then 3 years later, there was the discovery of the Ws. And then some months later, discovery of Z0. And in 1984, the Nobel Prize in Physics was awarded to Carlo Rubbia. He's still alive. In fact, I saw Carlo in October last year. And Simon van der Meer, they were our leaders. He made sure that we can have enough antiprotons to have the collisions. And Carlo made sure that the accelerator was born, actually came into being. And actually, without Carlo, there will be no PP bar collider. And without Simon, there will be no antiproton to have. So quite rightly, they got the Nobel Prize for this. Right, how do I do that? You can do it.
Can I just to check, everybody is still, say your slide is still on, or? Are we share anyway?
Yeah.
So.
Okay. Okay, thank you. So I want to reflect on two things here. Is to now signal processing, so how often are these particles produced? Of course, in that context, there is only collisions. One event is a collision. So if there are 10 to the power 8 collisions on average, we expect one event in that configuration, in that experiment, which is a W boson. And as you know from signal processing, that's equate to minus 80 dB. And I want you to focus on this number minus 80 dB. I'll make some references later on. And when you say Z0, Z boson is about the same. It's a little bit less likely, but it's similar. So as you know, 0 dB SNR, meaning equal amount of noise and equal amount of signal, is bad. And SNR of minus 80 dB is really, well, it's not really, it's impossible. That's what people would say. But it wasn't impossible because we discovered it. So one might want to think, how was that possible then? And of course, there's no agreed thing. So this is my take on it. I think it's possible, it was possible because through excellent modeling. And I say one line after this, and careful experimentation. And when you're working with that kind of things, it's not enough. You need statistics. You have to be on top of statistics to be able to do these kind of things. So I think it's a combination of all these three that made it possible. And modeling is very, very important. And as you know, in signal processing, modeling is essential. There could be no prediction without a model. Of course, we can read tea leaves, or we can throw a coin or dice or whatever, but that's not the proper way to do prediction. So proper way to do prediction is to have an excellent, as good a model as you can get. And I think those three, for me, they contributed, they made what's impossible to be possible. The other thing I like to say is that, I said, sorry, I just go back simply here. And this is for younger audience. When I was, just before I was finishing my PhD, I had an offer from, I won't say the institution, but I had an offer from US to go to US. And I was going to go to US, but then I was thinking, what else can I do? And the US offer, it was also research. It was fine. It's a very well-known place. If I tell you, you all know it. Akram certainly does. And I think I would have written papers. I would have found new things. But they are nothing that's going to shatter the earth. Nothing so exciting. But this, I was looking at this possibility. But remember, I said we didn't know they exist, although we thought they might. And even if they exist, I told you a very famous physicist already said we'll find it. It's some reason. But I thought I was young enough then, or I was stupid enough. I thought I would actually won't go to the US. The other thing for US was that they pay me more if I go to US than staying here. But nonetheless, why do you need money for? So I think for younger people that, well, for everybody in life, it's not just about one thing or another. You have to make decisions. You come to crossroads and you have to make decisions. And I think it's important to learn. I'm not saying I made the right decision. That's not what I'm saying. But it is important to make decisions in the way that you can live with the consequences should things go wrong. And okay, that's that. So now sort of put the clock forward a bit. So I got, this is to do with communications. These are different ways, when we send things like here, or as an example, then we don't actually send at the, we send it at a much higher frequency simply because through the air, it is easier to send it so that there is not too much attenuation and many other things. So if you think about it, you speak and your voice is maybe kilohertz, maybe even less than a kilohertz, maybe 10 kilohertz, about that, It's not 50 kilohertz for a start. But this frequency is probably a gigahertz or something like that. So what is done is you've taken your voice, is moved up at a very much higher frequency, and then its transmission is good, and then at the other end you demodulate. So modulation is important, and all of this M stands for modulation. Modulation is important for that, and modulation is important for coding. But anyway, so there is a problem of finding out, differentiating how these are different. I'll explain. So if you don't know QAM, doesn't matter. So pretend there is a language, and this language has only 4 alphabets. These are the 4 alphabets. This is a different language. It's got 16 alphabets. And this is yet another language. It's got 64 alphabets. And you now got signals. And you have to tell, is it from a 4 alphabet language, 16 alphabet language, 64 alphabet language? Now, in this case, in this picture, is at infinite SNR, meaning no noise. And everybody in this room and everybody who is not blind in the world will tell you, this is 4, this is 16, this is 64. And we designed a system that also tell 100% accuracy that 4, 16, and 64. But that's nothing, because we can all do it. But now what I'm going to do, I'm going to add a little bit of noise. Remember, minus 80 dB is nothing like that. So the bit of noise is 15 dB. So it's not minus, it's plus 15 dB. And what happened, you see this one, and you can still, everybody can tell that's a 4-character language, 4 alphabet language. Here, okay, there is some overlap, but we'll still go with 16 alphabet language. You come here, no clue, it might be completely random. And nobody in the world will ever say it's a 64 language. There's no way to guess that. But the same algorithm said this is 100%, nothing special. This is 98%, it's probably nothing special. But look at this. It can tell you the same algorithm as the last slide, and this is 98% accuracy that this is coming from a 64 alphabet language. So that's sometimes, I'm not saying AI is always better, but I'm saying there are some things that AI can do much better than a human will ever do, not only can do, will ever do. Here, we have a bit more noise. It's 10 dB, so it come down from 15 to 10, but it's still plus, by the way. And this got a bit bigger, these circles, but it's still 4, you can see. No clue. Is it 16, 64, random noise? No clue. There's no clue here either. But look, still at 95% accuracy, the same algorithm can tell you this is 16 alphabet language and this is 64 alphabet language. So this is not just a question of AI. Of course, there's a lot of signal processing is in here involved. And that was published, I don't remember the year, but at least IEEE, which doesn't exist anymore, it became IET. They offered us a prize for this work in 1998. And this is to show the strength of AI. It's not to say AI is better than human, always. Human can do multitask. AI does not have such a variety. You have one AI do few things, not everything. And this is some book that we wrote. He was my PhD student. He was at Brunel. He came from Liverpool to here. So this is particularly useful if you're trying to tune into BBC, you know exactly all the frequencies or modulations. But if you're trying to listen into things like GCHQ does, and not just GCHQ, all the security kind of CIA and so on, then you don't know what they are. So you just receive signal and you have to figure out what the modulation is. So it's a blind detection or classification. And that's exactly what this can do. And now it's very different. It's not exactly engineering, but it's to do with genes. So I give a slight flavor of engineering. So this is a project that we did with here. So this person, DJ Roberts, he is a consultant, hematology consultant in Oxford John Radcliffe Hospital. And at the time, we were working on a joint National Institute of Health research program, a 5-year program. And what we are looking at is we want to know, sometimes we need to do clustering. And clustering, but the problem is that if you take some data, and this is the data set, let's say, and you use a clustering method, and you get a set of clusters, which you call partition 1, then if you try and use a different method with the same data, but a different method, you probably get a different partition, almost always. Now, they may be very similar, but they'll be different, and so on. So what happens if you take one data set and many methods? You get many different partitions, see different partitions. But truth is only one. So therefore, how do you go from multiple examples or person of truth to one? So that was the problem. And the other problem is that, some of these data sets, they're very difficult to create and work with. So what's happened is there are many different data sets, many different labs, and you like to learn from all of them, not just one. And then the problem gets even more complex. But fundamentally, it's the same problem. That is, given L data set and C clustering methods, you'll get R partitions, which is L times C. And when you get R partitions, you don't want R partitions. Truth is one. So you want just one. And that was the push. And there was at that time, nobody had anything to get that consensus clustering. So we developed these consensus partition matrices and various things and provided a consensus. And it went through, we had to invent a couple of new things here, and we actually ended up with that. And that is produced a very, very interesting set of results. But of course, now these things are done quite a lot. So this is, when is it? Anyway, it's probably about around, oh, there it is, 2013, so 12 years ago. And I show you an example, practical example. And we wrote a book on integrative cluster analysis. We said in bioinformatics, because that's where we were working then, we can actually delete that. And this book will still be useful for integrative cluster analysis. But let me show you an example in the, okay. So this is in breast cancer. So this person, A.L. Harris, he is a breast cancer consultant, also from Oxford John Radcliffe Hospital, and he's one of the top people in the world, actually, in this area. And this is one of his postdocs. And he was interested in our work, and he said, can we look at some genetic data of women? And they know they got breast cancer. So it's not a detection problem. What they're interested in, that maybe if we can find some genes which gives better prognosis. NHS already had some way of giving prognosis, but he thought maybe we can do better, just ask us to try. So we did, and we found some very interesting results. I'll show you. So first, there are many clusters. It's not just 10, it goes on. But I just took these 10 clusters, and here we created something which you might call kind of error, some kind of distance measure, and what you find without knowing these details. So when the distance is small, it's good. And when distance is large, it's probably nothing. So you can see that two smallest ones are here. But more than that, as you know, we used to do, not anymore probably, in exam results, we're looking for gaps between first and 2-1, and 2-1 and 2-2. So here we're looking for gaps. You see, they're not the same, but they're close together. These are all kind of close together if you look at this height. But there's a big gap between here and here. So these, we label them as good clusters. So that's a completely, opinionated word, good. But we looked at these two, and something spectacular we found. So I did explain. So remember I said different data sets. So these are the different, so each row is a different data set. So this is D data 01 to D16016. And they were created in different labs, US, Japan, Australia, UK, and there are some others. And they are over different platforms and many things that's different. But what is very interesting, remember these two clusters, one has 500 genes, the other has 600 genes. And x-axis could be either time or conditions. And you take all these genes and you work out their average response. And the solid line is the average response. And the height is the measure of that response. And this is the other clusters. You find the average, and the solid line is the average of the response of this in this data set. And what you're seeing is that if you put a mirror here, down here, and if you take this one, and you see this is a mirror image of that. Similarly, this is a mirror image. So pair by pair, they are mirror images. And we here at Brunel are so struck, I didn't know what was going on. But anyway, we calculated, and then I told my postdoc and student to do cross correlations and things. And remember, as you know, cross correlation is by definition is between plus minus one. Plus one means is perfectly, basically they're exact. Minus one means they are kind of exactly opposite. And zero means just no correlation and things in between. And these 16 data sets, meaning these 16 stars, they are almost all below whatever it is, minus 0.95. They're basically minus one, but these are experimental data, remember. And so we went to have a meeting in Oxford, and I showed them. So Adrian, the consultant, said, we have never seen this, we meaning in the breast cancer world. And I said, why not? Because this came from your data. We didn't, this is not our data. And it's not just his data, as I say, all around the world. He said, this is something to do with AI. He said, exactly, I'm not crazy. He said, because we don't look at things that look different. We look at things that look similar. And I said, we weren't looking for things that look different either. I said, what happened? Oh, sorry. What happened is we got these two clusters. So we just looked at those two. But to get those two clusters, we never required that they have to be different. All we had. So this is a place which has been missed by the whole world of breast cancer until then. So my message about AI is, there are many types of learning, but two main ones I would say. One is focus learning, so which is basically what the idea is, Francis Bacon's idea. You write a hypothesis on a piece of paper, you go and do the experiment to see if it's true. If it's true, you accept it, and if it's not true, you change your hypothesis. So that's I call focus learning. The other one, I would say Darwin. He had nothing. He wrote nothing down. He just went around the world on the voyage of the Beagle and so on, and he just looked at the world. And he came back, and suddenly it emerged in his brain that maybe there is something like this is going on. And AI is very, very good at doing explorative learning. While it's not to say focused learning is bad or anything, they're both learning and they're both useful. But AI is extremely good in doing explorative learning, much better than we are. But along this line, I would say probably, quite cheekily, I say Darwin was the first big data processor in the world. That's my, okay. I don't need, I don't need to read. So we basically generated, meaning we discovered two sets of genes, and they can give better prognosis, at least as best, and looks like they give better prognosis for breast cancer. So now I'm going to tell you about brains, well, the bit that I've done with brains. So I was Finland Distinguished Professor from 2010 to 14. And these things, they invite people from abroad for these positions. And they give lots of money, not in your pocket, but for the project, and multi-million pound. And they want you to do something. And they said, in this case, I'm to put together, do some blue sky research about brains. So I did. This is some details. We don't need to read everything. So the MRI images, they're very time consuming and very costly. So you don't get generally thousands of data from one experiment, So in this case, 29 subjects, and that's not big, but that's big. Well, it's big individually, it's big because it's a three-dimensional picture, lots of voxels. And there are half of them are females, well, as much as 29, half could be, and half of them are male. And they're all young, generally speaking. And their head is in the scanner, and they're listening to music. And they're different times, of course, but they all listen to the same music. And while they're listening, and there are different sets of bits of music they listen, they have to do two things. One, they say, is the music happy or sad? So that's the H and S. And if they like the music or dislike the music. So it's a 2 by 2. There are 4 combinations there and there. And it's very interesting that you have happy music and actually people don't like it. There are some happy music. And there are also sad music that people actually like. So it's quite interesting, the psychology point of view. And of course, we had neuropsychologists, we had neuroscientists, the people like me, the people from Department of Music, and so on. And this created a lot of data. And at the same time, we actually did the EEG. That was a technical challenge because you have a magnetic field, the head is stuck in there, and you want the EEG, and you have electrodes, right? So that was a technical challenge. But anyway, we did it. But what I want to show you is, it's too complex to tell the uninitiated. I'll show you very simple. So I'm going to show you a brain, and this brain is average of the 29 brains, so it's not a true brain, but it's the average. The other thing is that each of our brain is different sizes and shape. So you can't average just directly. So to do that, what you do is, those who do image processing have heard of image registration. So you take an image and create a reference framework. You create that. So each brain gets projected. It's a mapping. If you think about mapping, it gets mapped onto a reference brain. And then you do 29 maps. And once then you forget the real brains. You just take 29 mapped brains, and then you can do average because they match. And that's one thing to say. And the other thing is, I'm going to show you the response in this brain, e-brain, and I just color code. So blue means low response, and red means high response. And when the brain will rotate, because you can see all the way around, and when it does, I will ask you to focus on one area of the brain. Doesn't matter which area. You focus on one area, and as it goes around, see the color changing. And the color changing because the music changing. So music is influencing the stimulus of that bit of the brain, whichever bit you will be looking at. So it's a long video, but I won't do it for too long. This is synchronized, all 29 listening to this music. So you could see this is now blue, and then changing. Yeah, And this is the back of the brain, and this is the frontal lobe. Something happened with the music. I don't know what happened. I'm going to, now we have the license to go inside the brain. If you think of an EEG, you get what's on the outside. With MRI, you can go inside. And with the e-brain, you can really go inside. So I'm going to go inside. So somewhere, let me go forward a bit. Sorry about this. Oh, there. So you can actually see right inside how the brain, bits of the brain is responding. And the link is, okay, I'll stop, I think. So I said about the genes, and in genes we have to do cluster, and here you also have to do cluster because the brain is if you think of SNR, is very low SNR, is a very noisy place because even when you're sleeping, as long as you're alive, your brain is working. And even now, as I'm talking, it's not just you, everybody, your mind drift onto something else within a very short time because that's the nature of the brain, So to do clustering in genes, there are something reference points, and those reference points in the gene was all the in the brain. In that case, was that we all have the same genes, so we can go with the gene name and we have reference. Here, there is no genes, but there is an equivalent of gene, and because we projected onto a reference brain, so if you think about the world map, then each of these voxel is fixed reference. So voxels in this brain, mapped brain, is equivalent to a gene in biology. Because one time I did the biology work first, 2010, and started. And then, I used to go to Finland and come back. It's a 3-hour plane journey. And so you get bored. So I was thinking, can I use that somehow in here? And I just realized, yes, I just map it onto a reference brain, and then voxels become genes. And that's exactly, so we applied that clustering algorithm in here. That was developed for the Oxford work. So you already might have noticed signal processing in it as well as AI, because clustering is unsupervised learning. The communication, the QAM work is supervised learning. But here I want to bring together something else, which is very obviously signal processing and AI. So this is about condition monitoring of vibrations with vibration signals. And this is a picture of a setup in the United States. And CWRU is Case Western Reserve University. That basically some here we got some bearings, and we have to, there is the bearing data center. We have to tell the condition of the bearing, and there are many, it's a classification, many states we have to notice. And what we have, the data, is just the vibration data. That's all we have. And this data we didn't collect. It's not our experiment, but it's publicly available. You have to request it and you can use it. And that's what we do. And this is summary form. So there is this, I want to mention about this compress sensing, sorry. Oh. So compress sensing. So as we know, the analog world, the world is analog. You see me is analog, but this world is not analog, or that world is analog. So that's digital world. So somehow we have to take analog signals and digitize it. And that process needs, among other things, sampling. And sampling, 100 years ago, Nike told us that to do sampling, the sampling frequency must be above a certain frequency. And that certain frequency is twice the maximum frequency in the signal. Now, he wasn't wrong, but he was talking about all signal, any signal, not any specific signal. But what's more recently been discovered is that there is a class of signal, and often called the sparse signals. And these sparse signals, you can violate Nike's theorem, and you can still do a good job. And so what happened is, in bearing, things rotates. In all rotating machine, like wind turbine or anything that rotates, there is a natural kind of, if you like, periodicity in signal. There's a natural. And so I told my PhD student who was working in these kind of things, I said, look, why not try the compressed sensing approach and see what happens? And so we did, and this is the result. So compressed sensing kind of formalized about 20 years ago. It's this century stuff. And it's now being used a lot. And I think we're the first one to use in this kind of work. But anyway, it doesn't matter if it wasn't, but certainly one of the first. But what I want to tell you here is that this bit, CPDC, that's to do with AI. And the CS is to do with signal processing. And first thing I want to enthuse you is that if alpha is 1, that means it's the Nike's rate. What it shows is that you can go down into very small number of alpha, meaning a lot less data, and you do very, very well. That's impressive, But the other thing to say is that if we use, although it says CS, actually, yeah, without CS, but it's the same methodology, but without using this. We use all the data, 6,000 input, and we get this kind of accuracy. And if we use only 1/10 of the data, meaning not 6,000, but 600, but with CS, you get this. And remember, this is not only the one that matters, but it's similar, but maybe better, but similar anyway. But this is important, and you got a lot less variation. So this is a better estimate than this one. And also it takes less time. So the amazing thing is, here you got a combination. So if we use only AI and not CS, no signal processing, we'll be getting this. By combining signal processing with AI, you do a lot better. So my message to, again, younger audience, people in the younger audience, is that if you have a problem, you solve it. And if you solve it, don't stop. Maybe you should look for something that could do possibly better. And that's, and of late, meaning maybe last 7, 8 years ago, I've been doing a lot of work in image segmentation, and these are modern ways to do image segmentation, meaning using fuzzy logic, AI, and this kind of thing. And Professor Lay, who is visiting Brunel, I'm doing a lot of work with him. But I won't say anything about that. But I would say just a few slides about my latest interest. Well, I'm quite excited by it. So it's time series representation of polynomials. And what he basically says, I found out meaning I worked out that every polynomial of degree q can be represented by a time series of order q. So there is complete parity. Not only that, this is more interesting, that a q degree polynomial needs q plus 1 unknowns, because you got q coefficients and a constant. Yeah. But a q degree time series requires only 1 unknown as a constant. And because the q coefficients in time series, I worked out mathematically exactly what they should be. So if you got a billion degree polynomial, you have a billion plus 1 unknowns. But if I represent that by a time series, which I can, I will only have 1 unknown. That's the constant. So, and there is a whole lot of stuff that can be done. Like if we have polynomial data, we can find the degree of the polynomial, the additive noise, meaning noisy polynomial data, the coefficient corresponding to the highest degree, all to do with polynomial, we can deduce without using a polynomial model. We don't need a polynomial model to do that. So here is a mathematical description of them. I'm not going to go through mathematics. So this is a polynomial because n to the power I goes from 1 to q, and that's the constant term. I can write exactly a time series. I showed that this can be done. Again, 1 to q, you got lots of AI. So at this stage, between here and here, you got same number of unknowns. There are q of these and one of these, q plus 1, q of these and one of these. But I proved that this AI is actually given by that. They're just numbers. So I can tell you what they are even before you tell me any polynomial data. I can just give you those. And this is why I said that in time series formulation, only one unknown, that's this one. And by polynomial, you got q plus 1 unknowns. And this is a sort of artifact or something that comes out of that. If you look at these 4 polynomials, they're all parallel, so they're the 4 polynomials. You need 4 equations, but I can write them as one equation. And in fact, there are infinitely many parallel straight lines, as you know. So there are infinitely many polynomials you need to describe them. But I will use only a single time series. I'll describe all infinitely many polynomials. So here is the collapse of infinity into 1. Okay, so on these, and right, the COVID-19 been terrible. It's changed the world. A lot of people died. And among all that garbage and chaos, that was set me up for this. I had the question I had about polynomials and time series a long time ago in my head. But to do this kind of research, nobody gives you any money. So I never applied for any money. But when the 2020 came and we were locked down, I told my wife, right, this is what I'm going to do. I want to find out. And because I was working on my own, I ended up publishing 4 papers. This is the latest. And this is the earliest. And in fact, very soon I discovered quite a lot of results. So I published that. And that was simply the mathematics bit of it. And then I was saying, what can I do with it? And I realized I can figure out the degree of the polynomial, without using any polynomial coefficients. I don't need a polynomial model. And that's this paper. Then I realized I can estimate the noise power. So that's this paper, as well as the degree. And not only that, I actually produced this degree estimation is better than any degree estimation that's known at the time. Okay, so that's, if you want to know more, come to my seminar tomorrow. So closing remarks. So I think, confluence of AI, big data and signal processing can harness results of quality that are not possible before. And for big data, particularly heterogeneous data rather than a big data, complex data research, signal processing and machine learning are vital to enhance the significance and power of research studies. And for all young people, I would say we are in a very special and exciting period, and I hope you can take this field much further. Thank you.
Thank you. So we are taking questions or comments from both online and also say in person. Okay. Yeah.
Many questions, but I can't figure about it. Okay. Most important question to me, you define polynomial data. What data is called polynomial data? Because I'm working on data, but this is quite a new name on me,
Polynomial data that comes from, but that can be described by polynomial.
Which means data come on one dimensional. Because
in this case, it's a one-dimensional, yeah.
But in most of cases, when you do read,
I know, but that
one dimension.
Yeah,
when you talk about the breast cancer, you also associate the patient age.
I know, but I defined what it is. Yeah, I know.
Okay.
It doesn't answer the world's problem, no.
Okay,
No problem.
Yeah, so
Big data and done.
how to define the degree of polynomial given data? Q,
Yeah,
it's how to define the Q.
read the second paper and the third paper, you get the answer. And it's better than anything that exists in the world today.
But that's interesting. You prove the equivalent between polynomial for order Q to AR
Yeah.
times sorry,
Yeah.
right? Why not feed the data directly by AR model?
Yeah, but we share model. That's the thing. That's exactly what I do. But come tomorrow.
Okay,
Find
come
out.
tomorrow.
Yeah, because there are more things. Some of these will be answered.
Yeah, but that's a quick question. Okay, just final question. You define AI as detection structure, detection rules, or forecast.
Yeah.
But most important thing in AI is to train machine to carry out the task or jobs which is like a human being with human being intelligence, right?
Yeah. Well, I don't know
That's not
what's
that they
important.
cover this,
Well, it does, because the thing is, you have to, basically, you're trying to get some things done, some tasks done, whether it's recognition, interface recognition, or what's going to happen, prediction. And it's just being, AI is an adaptive filter. And except it's a nonlinear adaptive filter. That's what it is.
But you cover a lot of data with literature, but one thing in signal processing, from my point of view, the data come like a sensor, come streaming data.
Yeah.
If they come
Online,
run all the time.
yeah.
You must be applied to that. Take account of the data coming.
Nothing can be applied for everything, so don't get too excited about it. But it can be done for offline, yes. But if you do want to do online, then you have to organize a smaller complexity variant, There is nothing in the world that applies to everything in the world, right? So don't get too excited about that.
Your method can be applied to that.
It can be, but the
Can be
thing is,
very
you need to-
effectively because big data is one thing,
Yeah,
but you can get small data, which is
exactly.
fast data.
That's what I'm saying.
which is
So
what you,
you can segment and you
That's
can
right.
try. Some of the people, there's a group in, I forget, China, or they both contacted China and Thailand, and they're using Kalman filter
Yeah.
for prediction. It's a polynomial Kalman filter called APKF. What's that? Adaptive polynomial Kalman filter. And the polynomial, reading our paper, my paper, they changed the polynomial with time series. And
That's
what
right.
he said, it's exactly that there are different kind of ranges of time, the different models, and it's adapting to that. So it is that. So, but in any case, as you know, in any case, if you want to do online estimation, you want something that's a bit quicker and so on, but yeah.
Yeah, now, a lot of industry looking for our students who are able to produce method to do OLAP online
Yeah.
process,
Yeah,
dealing with streaming data.
of course.
The data coming without stopping,
Yeah.
how to do this, do that.
Yeah.
Yeah. Thank you.
You're welcome.
So when you went to the condition monitoring part, you mentioned the compressed sensing, but you didn't mention what AI model it was.
Oh, is that a CS? There are many bits to it, as you know, but basically at the core of it was SVM. But it's not just that. We needed to, it's like feature selection. So they've got different names now, so you need to size up the feature space. And so there are the 3 steps. The last step is the SVM at the core of it. But I think SVM is not so special. What I mean is that, in all of these things, there are, if you think in terms of Lego a little bit, so you can change it to other things. It may not be as good performance, but it is the structure. In this kind of things, actually, the structure that's actually more important than the specific.
I think you mentioned signal, right?
Yes.
Which has like harmonics, as you mentioned. So why not using other type of the signal, like current data,
Like what?
like current or
Current.
yeah,
Because there's a bearing, there's no current there. You know, I'm just listening.
You mentioned the impact, like the condition of the signal due to the bearing damage, for example.
Yeah.
It will affect it.
But yeah, I mean, obviously one can look at the current, but here we're just listening to the bearing. You know, any rotated line in your car, it turns the engine on, and you can hear it.
Yeah.
Not Tesla or something, but you can hear it. And so what's happening is that anything that rotates, it produces an electric fan.
Yeah.
You put the fan in your house or wherever you have one, it's noisy. You know this. So the good thing, if I want to know if the glass is broken, I have to actively hit the glass, and then I can hear the sound. In a rotating machine like a bearing, it just produces, so you just capture it. You don't need to excite it because it's self-excited, if you know.
Well, it's in a noisy environment.
Well, they are in noise. Yeah, obviously it's difficult. Yeah. Obviously there will be a amount of noise, it's very noisy, and you can't do it. Well, that's not surprising. That's what life is. You do as much as you can.
Yeah. Thank you.
In 20 years, people will come around and do everything better than you do. So, but that's not the reason not to do anything. Oh, well, somebody else do better. You do what you can.
Any other questions? Yeah, let me just check those people online. Do you have any questions? Either you could say shout through your microphone or leave a message in the chat window. So we got a comment from RF. So a very varied, interesting, and presumably highly rewarding career. Well done, and thanks for the presentation. Question regarding comms modulation. Have you come across AI/ML in the formation of novel, highly complex modulation schemes beyond QAM and QPSK?
Yeah. You just type in yes.
It just right. So are you happy with the Prof. Nandi's answer? RF. Yeah. Other questions?
By the way, I'm not, well, I hope it doesn't sound like that. I'm not, because it came out. So
Could you please
expand? Okay. So I don't.
You can today.
Oh, I can just say. Okay. So, okay. I don't actually work on it now, but I was the first person to bring AI into modulation recognition. Before then, they were all kind of feature-based or expert systems, and my first paper was exactly 30 years ago, 1995.
I think that's a constellation design.
Yeah.
Is my understanding is correct?
That's
They are asking for constellation design.
Oh.
Around QAM and QPSK. Have you come across in the formation of novel?
All right. No. Not in the formation. I wasn't sorry.
Design,
so
but in the
I didn't work on the formation of the constellation design because my push was not how to do more difficult constellation to be recognized or this kind of thing. My push was I can listen and I want to figure out what it is. So not designing a new way of doing it, but it's there and I'll only listen and I'll tell you what it is.
Does that answer your question, Mr. RF or Miss RF? You hear us? You just wait for the message. Oh, well. Any other questions? Okay, so for those who come, thanks. Okay, an interesting subject.